Hey guys, we're going to talk about areas, using limits to find areas. You need to sit back, relax. This may be one of the longer ones we've had all year. Sorry about that up front, but it's quite a bit of work to get through this stuff. I'm just going to tell you that up front, just to prepare you. And the problems that we're going to be doing, this is one of the central problems in calculus, is finding area under a curve. And here's what it looks like. Quick sentence here: limits are needed to find the area of a region under a curved boundary. Think about it, and also, well, we'll get that in a second. Think about your geometry when you're found areas. Like, you know how to find areas of rectangles, triangles, polygons, stuff like that, but never areas of stuff under a curve. Think about how many curves you found the area of, and you found none of them. Okay, so using limits, the question becomes, can we make it precise? Can we get the area exactly if we're doing area under a curve? Let me show you what I'm talking about. For example, this picture. The base goes from A to B down here. Let's see, the heights are different here, heights different there. It's not really shape, and you got this area under a curve. So what we're going to end up doing is we're going to be drawing a bunch of rectangles under here. Okay, now these, I know you're thinking those aren't rectangles because the top's curved. You're right, but if I were to extend it, like, there's a rectangle, 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 and obviously that is not going to give me, if I find the area of each of these rectangles, it's going to give me an approximation of the area under the curve, but not the exact area under the curve. And hopefully it's making sense to you that the more of these rectangles I can draw, like I just drew 1, 2, 3, 4, 5, 6. Let's say I drew 60. If I drew 60, that'd be much smaller, much closer together, and also much closer to the actual curve. The more you draw, the closer you get. Okay, so think about that. The more you draw, the closer you get. Think about limits. All right, this one says use rectangles to estimate the area under the parabola from 0 to 1, and for y equals x squared. Y equals x squared is a basic parabola. Starts at 0, 0, goes up, goes through 1, 1. We know that's the point right there, and we're going to use rectangles to find the area. I'm just going to take you through this kind of step by step, like your book did. So obviously I copied this out of your book, but it's actually a really good example. Okay, so we're going to try to find the area. So what I did first is I split up into 4 rectangles. Okay, so I went 1/4 of the way, half of the way, 3/4 of the way, 1 of the way. And I drew the triangles. And here you can see the triangles. Now when I did the triangle, so I keep saying triangles, they're rectangles. Okay, I took it from the right side of each one and drew it that way. Right side, that way. Right side, that way. Right side, and drew my rectangles. That's where this R4 comes in, because I did it from the right. You could also do it from the left, which we'll do in a second. You'll see what happens. But each one of those triangles, think about it, the base rectangles. I keep thinking I say rectangles. Okay, the base is 1/4. The height is the y coordinate, which is, remember, this is y equals x squared. So the y coordinate is going to be whatever x squared is. So 1/4 squared. And then I'm coming here. 1/4 times 1/2 squared. 1/4 times 3/4 squared. That's this one. 1/4 times 1 squared. And if you add all those up, that gives you the area of all those rectangles, which means we're going to estimate the area under the curve as that. Now you can tell, hopefully, that area is way too large because our rectangles all went outside of the curve. So that's a little bit too big. So now I'm going to do the same thing, except pretty much go to the left. So instead of drawing the rectangle, when I do this first one right here, I'm going this way. Draw the other one, go this way. Other one, and you see what's happening. It's going to be a little bit short of the area, but I'm going to find the area the same way. The first one right here, 1/4 times 0 squared, because there's no height right there. Okay, then from here to here, 1/4, and again, 1/4 is the left side, times 1/4 squared. Right here, 1/2 is the height here. 1/2 squared is still 1/4. It's 1/4 every time because the base is always 1/4. The height's what's changing. Height's 3/4. Notice I'm using the left side of the rectangles this time. When I do the left side of the rectangles, I'm getting this. So think about limits again. All right. What's it approaching from the left and the right? Is it approaching? What numbers is it approaching as you look at it from left to right? So I know the area is between those two numbers. Okay, because this is what I got on the right side. This is what I got on the left side. All right, so what I did is now I broke it up into eighths, and did the same thing. And then you can see my little table right here. And what I did is I kept on breaking it down into 10 rectangles, 20, 30, 50s, all the way up to 1,000. I actually got a computer to do that, obviously, and I copied out of your book. But that's what happened. And look what starts happening with the left and the right. Look what they both start approaching. down here. Okay, so they both start approaching point 333, you know, stuff. So what we do then, because when it's so big and it's approaching point 33, we're going to use the limit of an infinite amount of rectangles of the area of an infinite number of rectangles and say, well, that area of all those rectangles put together is 1/3. And so here's what we're going to say. The more rectangles we make, the more precise our approximation. So we're going to do a limit all the way to infinity to try to be as precise as we can be. All right. Probably the most important slide of the day is this one right here. It says definition of area. I hope you followed along really well. I really want this stuff to make sense, like what we're doing. Because when you see the problem in a minute, you're going to want to pass out on how it all plays out. But the most important thing today is figure out, okay, what is we're doing? We're trying to find the area under any kind of curve. And here we go. It says the area of a region that lies under the graph of a continuous function, which means a curve, is the limit of the sum of the areas of the approximating rectangles. That's what we just got finished talking about. Okay, so here's how that limit's going to work. We're going to say the area is the limit of r as n goes to infinity. Right here is how it works. Okay, as n goes to infinity, the limit of f of x1 times the change in x. Now, I'm going to come down here and show you what that's talking about. Look at my x1 right there. Okay, that line right there is the height at x1. Okay, so how do you find out what that height is? You plug it into the function. That's what f of x1 means. Like the one we did a minute ago was y, or f of x, just put f of x equals x squared. And the way we found out what the height was every time was I just squared whatever the x coordinate was, because that's what the height was, because it's just x squared. All right, so just plug the number in. So f of x1 represents the height. The change in it, the delta right there, the delta x, I just wrote all over it. The delta x, that symbol's delta, that means the change in x. How much is x changing? Which is the base. Okay, so you got, or length, so you got base times height, and the summation, notice there's all these plus signs, until you get to the last one. And we're going, n's going to infinity, by the way, okay, of the last one. So using sigma notation is what we're going to do. We're going to write like this. We do the limit of the sigma of f of x k, notice, and times change in x, which is this represents the area of each rectangle. The n is basically how many rectangles there are, which we don't really know, and k is 1. Okay, so we're starting from 1 to n, and we're going to use this every time. If you write nothing else down from this video, that's what we're going to use on every problem that we do to find the area under a curve. It's called the summation way of doing it. There are actually 3 ways to do it, and if I'm going to be completely gut level honest with you, this is the worst, but it's the one that you can understand at first. If you're going to take calculus, you'll find a better way eventually. I'm just going to throw that out there. I can't teach it to you yet because you don't know how to do derivative. Well, don't do integration, so here's what it is. Okay, the width. Okay, the width of every one of these, which is this. The way we're going to find delta x is we're going to do, you do b minus a. That's the whole thing. Look where the b is, look where the a is. That's the whole thing. So if you divide that by the n, by how many divisions, how many rectangles there are, that's going to be our width every time. B minus a, the ending point, minus the starting point, divided by n every time. The height is going to be f of x1, f of x2, f of x3. It's going to keep going like that. And then to find our area, which is the r sub n, that times the change in x, the height times the change in x, all the way to the n. Okay, so that's how we're going to roll. What I'm going to do is I'm going to show you an example right here in a second. This is going to finish up the video. Sorry it's been so long, but it is really important, and it's not easy. Okay, you have to have these formulas. So again, stop the video right now. Write these down. These are summation formulas. We actually proved these, believe it or not, when we did, I don't know if you remember, we did math induction. We were doing those proofs, like we proved one worked first, then we found the next term worked. We actually proved these. Okay, so I'm putting rectangles around all of them. You got to have these. You got to write those down. I don't expect you to memorize them. We will have them for you on your test or whatever. So make sure you have those. I'm going to go on. All right, let's try this thing. This one says find the area of the region that lies under the parabola y equals x squared, which is what we've been doing all day today, the same picture. But this time we're going from 0 to 5. So I drew a picture here to let you see what we're doing. There's that orange region right there is where we're trying to find the area of under the curve y equals x squared, which is a parabola. and we're going from 0 to 5 on the x-axis. That's what we're trying to find. Okay, I'm going to shrink it back down. To do that, we need to find the width first. We're going to use our definition. We're going to use that formula we had on the last slide. Okay, but to do that, we've got to find the change in x, delta x, and we need the f of x I or x n, whatever. Okay, so I'm going to start here. The width is all, you always find the width the same way. The width is always, I'm going to go back to the picture, is b minus a, b being the final point, a being the starting point, which is 5 minus 0. N means how many rectangles there are, which we don't know. We're going a bunch. We're going infinite, really. So 5 over n, that's our width. Okay, we're always going to take the width is always going to look like that. B minus a over n. All right, now the right endpoint, which is important so I can find my height or my delta x. I'm doing this. So that's the xk is always your starting point, which in this case is 0, plus k times delta x. Okay, delta x is the change in x, which is, that's the base. That's how's your x changing. And we're going to do that however many times that happens. So k represents how many times x changes throughout the problem. So it ends up being 0 plus k times 5 over n equals 5k over n. Okay, now that's important because that right there, the right endpoint, tells us how to find our height. Now the height, remember, is f of xk. So what I'm going to do is I'm going to plug in the 5k over n into function f, which is right there, which means I'm going to square it. And if I square 5k over n, I end up with 25k squared over n squared. So now that I have this, the f of x sub k, and I also have the width, which is delta x, 5 over n, now I can just set up our definition and we can go. Okay, so I'm going to write this down. Just take your time here. The area is going to be the limit as n goes to infinity of the summation of k equals 1 to n. That's going to be true every time. Of f, this is our definition, xk times delta x. Now I'm just going to plug stuff in here. Okay, so I'm still going limit as n goes to infinity of the summation of k is 1 to n of, now f of x, we just found that out up here. That's 25k squared over n squared. And then delta x was 5 over n. So there's our, basically our first step, plugging that in. I'm going to move this up because it's going to take a lot of room. All right, keep going. The limit as n approaches infinity, same summation, k is 1 to n. I'm going to multiply this together. I'm going to get 125k squared over n cubed. I just did the math there. Now, you're going to do a whole lot of that. We're going to do a whole lot of a lot of math. Okay, so moving that up, move it up, keep going. Now, once you see stuff like this, the n is actually a constant. So is the 125. Okay, the n is up here. It's a number. N is going to infinity out here. Okay, so it represents a number just like 125 is a number. So one of our summation rules is we can actually factor out the constant in front of the summation. So I'm going to say limit, and we're going to do this a lot. I keep saying that. Of this, oops, not the k, of 125 over n cubed times the summation of k equals 1 to n of k squared. All right, now that's beautiful because I got the k squared there. I got a summation of a square, which means we have a formula for that. Remember I told you to stop the slides a few minutes ago, or stop the video and write down those formulas? One of them was for k squared. And this is where it's going to come into play, and it's going to come into play on every one of these that you do, because you're going to do a summation every time. So I'm leaving the 125 over n cubed out here. The summation of k squared is this right here. It's n times n plus 1, that's a 1, times 2n plus 1 over 6. That's the summation All right, and I got that from the other slide, and you will have those. If it's k squared, there's one. If there's k cubed, it's a different one. It just goes like that. So what I'm going to do next is I'm going to combine all this. Wow, this is going everywhere. All right, so when I combine it, I still have my limit as n goes to infinity of, make it one big fraction here. I have 6n cubed. Actually, this n and that n cancel, so I'm going to put n squared on my denominator. I have a 125. I'm going to go ahead and do FOIL here. It'll give me 2n squared plus 3n plus 1. Like that. Keep on working. I'm going limit as the n goes to infinity. Now, I can pull out the 125 over 6. And the rest of the time, I'm going to divide. So I have a 2n squared over 6n squared. Because all this... Okay, I put out the 125 over 6. That left the n squared in there. Okay, so I'm going to divide the n squared into the parentheses. So n squared goes into 2n squared. It leaves me a 2. This is going to be 3 over n. And that's going to be 1 over n squared. Right, so I'm getting really close here. Now I can just go ahead and do the limit. I'm going to start taking a limit now of what I have. So remember, the limit of a constant is itself. So I get 125, 6, that's going to stay. The 2 is going to stay because it's also a constant. Because the n's on the denominator and I'm going to infinity, that's a 0. Because n's on the bottom is going to infinity, that's a 0. Which gives me 125 over 6 times 2, which would be 125 over 3. You know what? That's a 120. I'm going to do that again. 125 over 3. That's the area. Which is about, by the way, if you punch it in your calculator, about 41.7. Guys, that's all there is to it. All right? I wasn't joking. This is big time. We're going to get through it. You got to trust me there. We always do. We always make it. Main thing in the video is make sure you understand what we were doing. We'll get the execution down the next couple of days. Okay, so hang in there. Don't quit. Don't give up. Don't ever give up. I'll see you in class tomorrow.